is the solution video to the Fall 2024 Calculus 1 exam from Oklahoma State University. This exam video can be used to study for exam ones, but just remember that watching these videos doesn't necessarily cover every single thing that you would need to, so make sure you're also going through the sections as well. Okay. So the first one says, answer the multiple choice questions. So here we are given three functions, f, g, and h. So I think it would be good to start by maybe graphing the three functions and seeing what they are. So the first thing I would notice about this one is that we can factor it. So for f of x, we can factor the top to be x minus 1, x plus 1 over x minus 1. So I can see that this x minus 1 is a removable discontinuity at 1. So at 1, we're going to have a hole in the graph. So this one will have a hole at x equal 1. And otherwise, it's going to look like the graph of x plus 1. So at the value 2, we will have a hole, and we're just basically going to have the graph of the line x plus 1, except that there's a hole at the point 1, 2. Okay, let's look at g of x. G of x looks like it is exactly the same as this function everywhere except x equal 1. So if I were to draw that, it's going to look like this, and it's going to have still that hole there. But it's defined to be the y value 1 at x equal 1, so it has this dot there. And then let's look at h of x. H of x is just equal to x plus 1, which would be basically that line, x plus 1, except it does not have a hole. So it's going to be filled in dot there. Well, or we could just not draw a dot at all. And so that looks like that. Okay, so now let's see if we can answer these questions. Is the limit as x approaches 1 of g of x equal to g of 1? So let's go over here to the function g, and I can see that, as x gets in close to 1, the y values are going to 2, but g of 1 is 1, so this is not true. Okay, the next one says the limit as x approaches 1 of f of x is equal to the limit as x approaches 1 of g of x is equal to the limit as x approaches 1 of h of x. And so we can see from that all of those two-sided limits exist, and they're all equal to 2. So those are all three equal to 2, so this B is correct. Part C says, is f of 1 equal to g of 1 equal to h of 1? Well, first of all, f of 1 is not even defined. G of 1 is equal to 1, and h of 1 is equal to 2. So those three are not equivalent, so we can cross that out. This one says the functions f and h are continuous at 1, but the function g has a removable discontinuity at 1. So it is true that the function g has a removable discontinuity. That part is true. But f is not continuous at 1 because it has a hole there. So D is not correct. And then the last one says the limit as x approaches 1 of f equals the limit as x approaches 1 of h, but it's not equal to the limit as x approaches 1 of g. And that is false because the three limits are all the same. The y values are approaching 2. The only difference is that in g of x, the actual function is defined there, is just not equivalent to the limit. So the correct answer for that one is B. All right, let's look at the second one. An object is moving forward along a straight line. The distance the object has traveled in meters from its starting position t seconds after it started moving is given by s of t equals 2 square root of t. The question is, what is the average velocity of the object over the interval from t equal 4 to t equal 9? So what we need to do is we need to compute an average velocity. So average velocity will be equal to the change in position over the change in time. And I'm given two specific time points, time t equal 4 and t equal 9. So I'm essentially looking for s evaluated at 9 minus s evaluated at 4 divided by 9 minus 4. And so if I evaluate the function s at 9, that's going to give me 2 times the square root of 9 minus 2 times the square root of 4 over 9 minus 4. So the square root of 9 is 3. That's going to be 6 minus the square root of 4 is 2. 4 over 9 minus 4 is 5. So this gives me 2/5. So the correct answer is D. Number 3 says if f and g are continuous functions, and we know that f of 5 is equal to 5, and we know that the limit as x approaches 5 of 2 times f of x minus g of x is equal to 6, I want to find g of 5. Okay, so one thing we need to note here is that they're both continuous functions. And so what that means is that the limit as x approaches 5 of f of x is equal to f of 5, and the limit as x approaches 5 of g of x is equal to g of 5. So what that means is that the two-sided limit exists, and the function value exists, and the function value is equal to the value of the function. So the only one up here, if I look back at the first one, is h is continuous because the two-sided limit exists, the function is defined, and the y value of the function is equal to the two-sided limit. So that's what we're talking about when we mean continuity. This one is not continuous because the two-sided limit is going to the y value 2, but the y value of the function is 1. This one is not continuous because it's not even defined at x equal 1. So we're dealing with continuous functions here. So let me clear a little bit of space and we'll work through it. And so we're also going to utilize our limit laws. So you can kind of see this is the case. So I know that the limit as x approaches 5 of 2 times f of x minus g of x is equal to 6. Let's break up this left-hand side using our limit laws. So using our limit laws, I could say 2 times the limit as x approaches 5 of f of x minus the limit as x approaches 5 of g of x. That's just using my limit laws. Still equal to 6 on the right-hand side. And now I know this value, that the limit as x approaches 5 g of x is g of 5. So I can just replace that there. So this is g of 5. And I also know that this limit as x approaches 5 of f of x is equal to f of 5. And so then we also are given that f of 5 is 5, so we can replace that as well. So 2 times 5 minus g of 5 equals 6. And now I can solve for what I'm looking for, which is g of 5. Okay, so let's go over here. So I get 10 minus g of 5 equals 6. I can add the g of 5 over and subtract the 6. I'll get 10 minus 6 is equal to g of 5. So g of 5 is equal to 4, which is the first answer here. So A is correct. All right, so the next one, it says the temperature in degrees Fahrenheit of a 12-ounce cup of coffee at time t is given by this function here. And this function is valid for times between 0 and 10 minutes. So then it says, what is the most appropriate interpretation of this statement? So I'm given that the derivative of the temperature function evaluated at 4.2 is equal to negative 9.58. So what that's saying is that after 4.2, that 4.2 is an input, which would be a time. The time here is measured in minutes. And then I'm given that my rate of change is negative 9.85. So what would be the units of that? Well, I can look at the Leibniz notation to tell me the units. It's going to be degrees Fahrenheit per minute. So what that's telling me, the negative is telling me that the temperature is decreasing. And if I think about a cup of coffee, that makes sense because it will be cooling off. So I can say the temperature of the coffee is decreasing by about 9.85 degrees Fahrenheit per minute. So for each additional minute, it's going down by about 9.85 degrees Fahrenheit. So let's see if one of these matches that understanding. So the first one says 4.2 minutes after the coffee was brewed, the temperature of the coffee was 9.85 degrees Fahrenheit less than the initial brew temperature. So there are some elements of that are right, but it's not that much less than the initial amount. That's telling you a rate of change. So A is not correct. Let's look at B. The temperature of the coffee decreased by 9.85 degrees Fahrenheit during the 4th minute after the coffee was brewed. Now that's a little bit closer, but we don't know that it's kept that rate of change for the whole minute. So it might not have decreased exactly that amount. That's why I say it's about 9.85 degrees Fahrenheit for each additional minute, but not exactly because the rate of change is not constant. So we're going to cross out B. C says, on average, the temperature of the coffee decreased by 9.85 degrees Fahrenheit each minute after the first 4.2 minutes. So that is, it is recognizing that the 9.85 is a decrease in temperature, but it's saying, it's kind of thinking about this in terms of a constant rate of change, that it's, that's an average rate of change. That's not an average rate of change, it's instantaneous. On D, it says 4.2 minutes after the coffee was brewed, the temperature of the coffee was changing at a rate of negative 9.85 degrees Fahrenheit per minute. That's the bingo right there. Let's just read the last one just to be sure. The temperature of the coffee was approximately 132.01 degrees Fahrenheit, exactly 4.2 minutes after the coffee was brewed. It's not clear where that number came from, although it seems like they may have plugged that in to this function here and found a value for the temperature. So E, it might be true, but it's not giving us anything about an interpretation of this statement, which is what we were asked to do. So even though E might be true, I actually don't know. I didn't plug the number in, but E is not the correct answer. Okay, the 5th one said, Alessandra is traveling down Interstate 35 at a constant velocity. For every 10 minutes in the number of minutes X, for every increase of 10 minutes in the number of minutes X since she passed the mile marker 174, her distance Y decreases by 7 miles. Which of the following statements is definitely true? Okay, so what this is saying is that her change in Y, distance from Oklahoma City, is equal to negative 7, right? And then it's saying that delta X is equal to 10 for every increase of 10 minutes. So X is for minutes. So we could say, delta Y over delta X is equal to negative 7 over 10, which I can rearrange that to say delta Y is equal to negative 0.7 delta X, which is where that comes from. So A is correct. B is saying that is using that 0.07 as and not kind of treating it like a rate of change. They're saying like Y equals negative 0.7x. So this would only be true if, so this actually doesn't make a whole lot of sense at all, because what does Y stand for? Y stands for the distance from, distance to Oklahoma City, right? And this is giving us a negative value for that distance, which is not really making sense. So we're going to cross out B. C, X is approximately equal to negative 1.43Y. So that might be the number that you get if you flip the fraction. But again, you're making the same error as you're making on that one, which is, that's not really what Y means. In other words, it would have some initial value of distance from downtown Oklahoma City, when you're at mile marker 174, you're some distance away from Oklahoma City, and then you're decreasing that amount. So it's also missing kind of like an initial value. So the only one that's true is A, and so D and E are also false. Okay, let's keep going. This one says, Pistol Pete was cheering on a cowgirl basketball team and threw a team jersey into the crowd. The height of the jersey above the arena floor is given by the function h of t. Describe the meaning of the following expressions in the context of this situation, specify units, and so on. Okay, so h of 2, this here represents the height after 2, what are our units here? Seconds. And I'm subtracting from that the height after 1 second. So in all, this thing represents the change in height of the jersey in feet from t equal 1 second to t equal 2 seconds. So it's telling us how much the height of the jersey is going to change in feet. So I have given the quantity represented. The quantity is change in height, and the units are feet. So that expression is going to be measured in feet. This one here, I'm taking the change in height and I'm dividing by a change in time. So this is telling me the average rate of change in the jersey's height, and that average rate of change will be measured in feet per second from t equal 1 second to t equal 2.5 seconds. Okay, this next one is that looks like a limit definition of derivative here. So this is actually equivalent to h prime of 1. So this tells us the instantaneous rate of change of the jersey's height and it's measured in feet per second at t equal 1 second. Another way to say it is it's the speed or velocity of the jersey in feet per second at t equal 1 second. So either of those answers would work. The next one says, what does the solution to the equation h prime of t equal negative 3.2 represent? So first of all, let's think about this. That is giving us a rate of change, and then we're trying to solve for it, so that would be the thing we're solving for would be the time. So this would be the time in seconds when the jersey is, and so the negative means the jersey's height would be decreasing. So I'll say falling at a rate of 3.2 feet per second. Okay, so looking at this one, I'm given a graph, and then I need to evaluate these limits. So the first one is the limit as x approaches 5 of f of x. So as x approaches 5, that's here. It looks like from the right, it's approaching the y value 3, and from the left, it's approaching the y value of 1.5. So since the left and right hand limits are not equivalent, this two-sided limit is d in e. The next one says the derivative of the function evaluated at x equal negative 5. So if I look here at negative 5, this is actually a linear function, so I can actually compute the slope of the function at x equal negative 5. So it looks like the rise over run would be rise of 1, run of 1. So this is going to be a slope of 1 over 1, which is just equal to 1. The next one is, so the notation looks a little funky here. What's meant is f of 5. So that's what's intended to be there. So when I'm looking for f of 5, notice it has this kind of jump discontinuity. So I'm looking for the filled in dot, and I see that filled in dot right there. So f of 5 is equal to 3. The next one says the limit as x approaches -2 from the left. So if I'm approaching -2 from the left, that's this way. What is the y value approaching? It looks like the y value is at 2 there. The next one is the limit as x approaches -pi of f of x minus f of -pi over x minus pi. This is the definition of derivative. So in other words, this is f prime at -pi. So what is -pi? So -pi would be about -3-ish. And if I look at that, I can see that that is a horizontal line there. So the slope there is 0. The next one says the limit as x approaches -4 from the left of the derivative. So what I'm looking at is the derivative, which would be the slope of the tangent line, as I'm approaching -4 from the left. So as I'm approaching -4 from the left, the slope here, I already computed it. I think I computed that slope was 1. From the right, I can see the slope is 0. So so if I were asked for the limit as x approaches -4 from the right of df dx, that would be 0. So I can see that the derivative is not continuous there at -4, which is, we have this like cusp kind of thing, so it's not differentiable there. That was just a side note. Okay, the next one I'm looking at, again, this is going to be a derivative, so this is going to be f prime of 4. So let's, f prime of 4, of -4, excuse me. F prime of -4. So f prime of -4, since the left and right hand slopes are not the same, since there's a cusp or kind of like a spiky point there, this derivative does not exist because the left and right hand slopes are not matching up. Okay, next I'm looking for f prime of 7. So I can look at 7 here. I can see this is a linear function, and it looks like our rise is a half and a run of 1. So the slope there is 1/2. The next one is like an average rate of change for, between 5 and 7.3. So 7.3 would be in here somewhere. So basically I'm looking for the slope of this line, which I just found to be 1/2. Then it says list all the values of x in that interval for which f is continuous but not differentiable. So we're looking for it to be continuous. In other words, I can kind of trace it without picking up my pencil. It's kind of a way of thinking about that, but not differentiable. So we found that it is not differentiable at -4, but is also continuous there. So x equal -4 is an answer. Let's see if there are any others. At -2, I can see it was not differentiable, but it's also not continuous. Then it's continuous and differentiable. We've got these kind of smooth curves. That's all good up until we get to 5. At 5, it is not differentiable, but it is also not continuous. So the only place where we really have an issue where it's continuous but not differentiable is at x equals -4. All right, next one. I'm supposed to evaluate these limits. So I'm looking for the limit as x approaches 4. The first thing we want to do is just see, like, is it continuous? Can I just plug in 4, or do we have a problem? Well, I notice that as x goes to 4, that denominator is going to 0. So I'm going to have to do something maybe algebraically, try to do something algebraically to get rid of that x minus 4 in the denominator. The first thing I might notice is I can factor in x out of the numerator. So I'll have x squared minus 16, and then x minus 4. The next thing I can notice is that x squared minus 16 is a difference of squares, so it will factor. Now, I'm going to write an equal sign here, but I need that limit as x goes to 4. I need to keep writing that limit until I take the limit. I haven't taken the limit yet. So this factors into x minus 4, x plus 4 over x minus 4. So now that's what I wanted to see, that this x minus 4 can divide to make 1. And so that is going to be equivalent to the limit as x goes to 4 for the function x times x plus 4. Now, again, I need this limit here until I evaluate it. Now I have a function that no longer has that x minus 4 in the denominator, so I can go ahead and evaluate that limit by plugging in 4, because this new function is now continuous at 4. So if I plug in 4, that would be 4 times 4 plus 4, which is 4 times 8. The next one, I'm looking for the limit as x approaches 2 of, I have this polynomial over x minus 2. So what we might think about is, can we factor this? Do we have a similar situation? So if I look at the numerator, I can see, let's see, so maybe x minus 2, x plus 6. Let's see, does that work? I'll get x squared plus 6x minus 2x, so that gives me the 4x, and then minus 12x, yes. X minus 2. So again, this one has a similar issue where I can get rid of that, and so then this is the limit as x goes to 2 of 6 plus x, or x plus 6. And now I have a function that is continuous at 2. I don't have that x minus 2 in the bottom anymore, so I can go ahead and evaluate that by plugging in 2. So I'll get 6 plus 2, which is 8. Okay, so for the next one, I want to use the definition of derivative to show this derivative rule that I'm given here. So I need to use the definition of derivative. So that's the one that looks like this. I want to take the limit as h goes to 0 of f of x plus h minus f of x over, well, it's basically x plus h minus x, which is going to give us just a plain h in the denominator. So let's plug that all in. So if I plug x plus h in for x, I'm going to have 4 minus 1 over x plus h minus, and then I need to subtract off f of x, which is just 4 minus 1 over x. Okay, let's see what's going to happen here when I do some simplifying. I have 4 minus 1 over x plus h, and then I'll have minus 4. So the plus 4 minus 4, those guys end up going away. And then that minus distributes, so I'm going to have plus 1 over x, and all of that is over h. Now I can't just go ahead and straight compute this limit because I have that h in the denominator and h is going to 0, so that is a problem. So one thing I can do is I can multiply to get rid of these denominators. So I'm going to multiply the top and bottom by x times x plus h. And so in doing that, I'm going to clear out those denominators in the top of the fraction here. So when I do that, that x times x plus h is going to multiply by, so all of this is going to multiply by both things. So when I multiply it in here, I'll just write it all out. So I'll have minus 1 times x plus h over x plus h. Then I'll have plus 1 times x plus h over x, and all of that is over h. So what's going to cancel here? So I can see that x and that x go away, so that divides to make 1. This x plus h and that x plus h go away. So now what am I left with? I've got the limit as h goes to 0. I'll have a negative x on top, and then a plus x plus h. All the bottom, oh, sorry, I've got this, I didn't write it here, but here it is. So this x times x plus h is multiplied by the top and bottom here, remember? So I've got that still in the denominator. So I'll have h times x plus h. Okay, and now I want to simplify. In the top, I can see I have a minus x plus x, so that goes away. And then I have this h divided by h, so those guys divide to make 1. So what's left? I have the limit as h goes to 0 of 1 over x times x plus h. Now, I no longer have that plain old h in the denominator, so I can let h go to 0 at this point. So that will be 1 over x times x plus 0, which is 1 over x squared, which is what I was shooting for. So, all done. Okay, for the last one, it says I just need to compute these derivatives. So we're going to use the power rule here for a lot of these. So let's go ahead and do it. So f prime of x will equal, so I'll have negative 3 times 9x to the 8th. And then I'll have minus 4x cubed. So that's the first one. For the next one, I think it will help if we rewrite our y this way as 5x to the minus 2 plus 8x to the 1/2. Now that I have it written that way, I can apply the power rule. So at this point, we'll take the derivative. So I'll have 5 times negative 2x to the negative 3 plus 8 times 1/2 x to the 1/2 minus 1, which will be negative 1/2. Okay, and then for the last one, I think again it will be helpful to rewrite what we've got here. So g of t is equal to t to the minus 4 minus t to the e, remember e is just a number, plus pi. Again, pi is just a constant. So let's find dg dt. Well, so that will be negative 4t to the negative 5 minus, here the t is the base and the power is e, so we're going to use the power rule. So that'll be e t to the e minus 1 plus the derivative of pi, since it's just a constant, is 0. And that's all.